Okay. Now, just like the previous section, where we calculated sample size, we calculated sample size when the population standard deviation was known, but now we're going to do it when it's unknown. And this kind of presents a chicken and the egg problem. So if we remember from the previous section 8.1, when we calculated sample size using the normal distribution, then we used a Z alpha 2 score, and we used the population standard deviation, and we divided that by the square root of the, no, no. I'm thinking of margin of error. All right. Okay, so sorry, this was the Z alpha 2 score times the population standard deviation divided by margin of error, and all of that was squared. All right. So you might think, well, if we're going to do this with a student's t distribution, then why don't we just keep everything the same? And instead of a z alpha 2, why don't we use a t alpha 2? And then because sigma is unknown, we'll use the sample standard deviation, and we'll use the margin of error, and we'll square it, right? We'll just substitute for z alpha 2, we'll put a t alpha 2 in its place and substitute sigma with s. So why don't we just do that? Well, this creates a problem because how do you calculate this? Well, to calculate the T alpha 2 score, you need to run this in an inverse distribution function, and what is it that the inverse distribution function needs? The inverse distribution function needs degrees of freedom. And what's degrees of freedom? Sample size minus 1. So how can you calculate this T alpha 2 score using an inverse distribution function if you can't get degrees of freedom because you don't have the sample size? So because you don't have the sample size at the beginning, you can't get degrees of freedom. And without degrees of freedom, you can't use the inverse distribution function to get your T alpha 2 score. And without the T alpha 2 score, you can't put it into this equation in order to calculate sample size. Okay, so that presents a unique problem. So how do we deal with it in situations when sigma is unknown? Well, we can do both a rough estimate, or we can also do a better estimate. So let me show you what the solution is here as best as we can do with a rough estimate. So we take the formula for calculating sample size that we had in the last section. That was when sigma was known. And because we're doing Z alpha 2 scores, we're going to use a normal distribution. So we're going to take this equation and we are going to substitute for the population standard deviation, which is known. We're going to substitute the sample standard deviation in its place. And that's the best we can do. We're still going to use a normal distribution here, even though kind of we should be using a student's t, but we have no choice. So we're going to use a normal distribution here in order to calculate sample size. Now, this is a rough estimate. So how do you get a better estimate? Well, what you do is you take this value of the sample size, the rough estimate of sample size, and you use that to calculate the degrees of freedom. And once you've got your degrees of freedom, sorry for doing that. Once you calculate degrees of freedom, now you can calculate your T alpha 2 score and get a better estimate for sample size. Okay. So, um, so instead of being a one step process, it can be a two-step process to get a better estimation. And the next example, I'll show you, what this looks like in the wild, so to speak. Okay, let's go ahead and stop there with sample size when the standard deviation is unknown, and we'll look at an example next.